And then now just gonna gently put it into a slip. So do either right or left, your choice. No feet needed.
No feet.
So a little right and then a little twist.
The electric aircraft industry is full of a lot of things like this, really cool looking mock-ups that are fiberglass and scale, but don't actually do anything and probably will never fly. But this place is building this aircraft, and I'm gonna learn how to fly it.
So your pedals are brakes only. Yaw is twisting the stick there. So that's probably one of the most unique pilot training considerations. It takes some getting used to.
I'm not sold, but okay.
We'll get you there.
That was just one of many of the interesting things that I learned during my intensive training here.
Yeah, you can just stretch out with your feet out.
Yeah, trying to remember to relax the feet. But I think you got the right technique there with crossing the legs between them.
Reminds me to not hit them when I'm on approach.
What I did in the sim, I had them down, but I still couldn't. I still went for it.
Yeah.
It's really hard to fight that instinct.
I'm gonna learn how to fly the aircraft here and see the operation that these guys are doing to build probably one of the first functional, certified electric vehicles that are gonna be flying people and cargo sooner than you think. The team at Beta truly gave me unfettered access to tell this story and capture whatever I could from the perspective of a general aviation pilot. This is the second of a multi-part series, and we're answering as many of your questions as we can in these episodes. So I met Kyle, the CEO, and a lot of what I've heard about companies is that the culture starts from the top down, and it was very cool to meet this guy. He seems so chill. He's such a pilot's pilot.
So we're in the Beta production facility where we make electric airplanes. Up in the top here, we've got clean rooms where we make the safety critical flight computers, inverters, motors, harnessing, all the stuff that has to be in a really controlled environment. We have machine shops, composite shops, and everything flows down to this floor where we put together the composites. We take all those composites in commodities, wings, fuselage, tail, and this jig, put all those together, then it goes in the final assembly line where we put the fixins like seats and avionics and interiors all together, and it rolls out to Burlington Airport and flies over to New York to our flight test center, which is where I hope you'll go in a minute or two or tomorrow and see them flight testing our first production aircraft.
The last episode covered this test chase.
That might have been a little too much of an input.
It's a fly-by-wire system. We'll talk about that this afternoon. This is kind of where it all started. The company built it in about 10 months with, a team of about 10 people. But this was to prove the concept that, electric vertical takeoff airplanes are possible. And obviously, we build things a little bit slower and more deliberately now, with certification in mind. So after this, they kind of said, okay, this design, proves that electric aircraft can take off and they can fly. And we did that as a concept. And then from that, they basically went back to the drawing board and looked at multi-copters, compound helicopters, like all different kinds that you could dream up, all the tilt rotor and what we call lift plus cruise. So with the lift motors and cruise, and basically kind of help design what of those is going to be the optimum, most efficient for the mission that we're trying to do. And the mission we're trying to do is carry cargo long distances and land without runway independence. So get to not needing a runway, being able to use a helipad.
The initial testing and training was the CTOL, or conventional takeoff and landing version of the airframe, and I got to fly that in the sim before actually getting into the real airplane.
So this is where you want to hold whatever yaw input you think you need. Just try to lock that yaw input in, and don't try to make it perfect.
Yeah, so I'm going to let myself slip back to the center line.
You probably can go to idle instead of drag. There you go. You'll make the runway here. So just hold that yaw in, hold that right wing down, and then your brain should be focused on just the pitch.
Yes, I'm trying. Way off center line, I'm going to live.
You're getting there. Back to it. Nice. Just keep that twist in, keep that wing down, and then you can get on the brakes.
But before flying, I had a lot to learn about the systems.
Yeah, you can see these are some of our previous generation's lift props that mount on the 4 booms on the airplane. And then this truck we actually use to test those props. So we got 14 feet up, we got one of our motors up top there to spin those lift props, and then we can drive it down the runway at different airspeeds. Because helicopters are fundamentally different than the props that we use. These are fixed props. So it's more like a tail rotor on a helicopter, but nobody has a fixed, rigid 14-foot prop that they're flying at 100 knots sideways through the air. Fundamentally different problems than you see in helicopters, so therefore different solutions in all direct drive, no gearbox, no articulation of the blades. That's how we upgraded to the next design. So really this program taught us what not to do in VTOL flying. But we learned a ton about how to build stuff and test it and do it safely, and that's what the team's taken forward. So building our own internal flight test program from scratch using this as a pathfinder was definitely like key stuff to learn.
So here, tell these guys right here, they're actually balancing an electromagnetic rotor. So that rotor has a bunch of permanent magnets arranged in a Hallback array, and they're here measuring tiny little perturbations in it. And it's one of the magics of flying an electric airplane is it's super, super smooth. You don't have these pistons banging against each other. You have a magnetic wheel affected by electromagnets that turns the propeller. So it's really, really smooth. It's kind of eerily quiet.
I was impressed that these motors, or engines as we're about to learn, are built in-house, and this was an initial part of the briefing in the sim with Nate.
Just kind of orient you to the gauges here. So each of these clusters, your pusher cluster, you tap on it and it shows you the status of your motor A, inverter A, motor B, inverter A. So each engine is electrically two halves of an engine that are completely separate.
It's interesting to hear you use the word engine, because so many guys will talk about motors on airplanes, and it's like, it's not a motor, it's an engine.
Yeah.
But now we have a motor and we're talking about it like it's an engine.
So to be more specific, a motor in an electric engine is the stator and the rotor pair.
Okay.
You add the inverter. This is what the FAA has said. This is what they have said the terminology shall be in electric aviation. Is a motor is the rotor and stator pair. An inverter plus a motor equals an engine.
And if they fail, it's like having a multi-engine.
So we are a airplane single engine because we have one engine. Mechanically, it is one engine.
Okay.
But you get the electrical redundancy of like having a multi-engine type aircraft.
So it's like losing a couple pistons, but it's not sending metal all through the thing and destroying the rest of them?
Exactly.
Got it.
Yeah, it's like if you could lose a piston and the engine would still operate just at half power.
Right.
And in our case, it is basically, at a pilot level, it's half power.
Because the failed engine or motor isn't really being dragged necessarily.
Exactly.
Unless that had a mechanical.
Yeah, if there was a mechanical failure, that's why the FAA said, no, it's still a single engine, because you could have a mechanical failure that would take the whole thing out.
Right.
So they're not too, so it's not, we say it's fault tolerant, it's not fully redundant.
Got it.
You get a lot of the benefits and some of the concepts of flying a multi-engine airplane that you don't see, with normal engines. Obviously a little different than a conventional airplane. We got a pusher propeller design. In concept, pusher propellers are always a little bit more aerodynamically efficient than a puller. So it's an air-cooled direct drive electric motor. It sits in about this much space at the aft portion of the engine. So a super light motor, gives us 420 something kilowatts of power. And the aircraft itself is designed for range and cruise efficiency, so it's really slippery. So that also enables it to accelerate pretty quickly. Just to kind of get you used to, we'll do the flight controls check first. So you got your side stick there. This is a flight control synoptic. So you can see this is your stick inputs, my stick inputs, and then flight control position outputs. Okay. So go and just play with it and do full forward, left, right, kind of see how those move.
And just checking the box.
Yep.
These guys are a lot of.
So your pedals are brakes only.
Okay.
Yaw is twisting the stick. So that's how you see your yaw input there. So that's probably one of the most unique pilot training considerations. Yaw is in your hand. All your previous feet coordination is for
So
not.
the video gamers that are good at this would love it. I hated that, so I always got rudder pedals.
Yeah.
And I would disable this or not use it on the joysticks.
Right, yeah. It takes some getting used to, but it definitely drastically reduces the weight requirements. Everything in electric aviation is, such thin margins, so we try to reduce weight anywhere we can.
So by not having a control system sending...
Yeah, you're not adding a separate control system, is kind of...
I'm not sold, but okay.
Yeah, we'll get you there. It's a couple hours of flying it, doing crosswind slips and landings and stuff, and you kind of get used to it, definitely. But it takes some intentional thought as you try to learn.
There is a lot of. So is this the real airplane has this much pressure?
Yeah, it's pretty well calibrated to the real airplane.
That takes you got to really grip it to get that full twist that direction.
So, and another note on that, when we're doing crosswind landings, these aren't pedals.
Yeah, so feet
off feet flat on the floor until
you're
on the ground.
God, that I can see being a mistake that
intuitively you would make, eh?
Yeah, if you're resting your feet up here, you're naturally going to start putting pressure on.
If you're in a crosswind scenario and it's like, no, I need more rudder, like I could see like doing that.
For sure.
It's going to be a hard instinct to fight.
So that'll be, instructor's job is to be watching their feet and making sure. And what I do, as soon as we take off, I can just kind of cross my legs between the pedals, because once you're above 30 knots, you don't need the pedals anymore. Your rudders are effective enough.
Weird.
Yeah.
Okay.
I'll save the engine start process for the next episode where we're focused on flying the actual airplane, but for this one, I felt like it was good context now to share my first attempt at putting this thing into a slip, not using my feet.
We don't have flaps, we don't have spoilers, we don't have speed brakes. The only tools we have on approach to slow down is we have slips and we have our regen or drag. So roll the thumb wheel all the way back.
The regen?
Yep.
All the way back, yep.
So you'll see now you get the drag indications.
Yep.
So you use the prop, we slow the prop down to increase how much drag you get on the prop to allow you to descend a little faster. So you can see we're up to 1,800 feet a minute now.
Yep, and 895 indicated.
And then now just gonna gently put it into a slip. So do either right or left, your choice. No feet needed.
No feet.
So a little right and then a little twist. And you can feel how much side loading you get.
Oh, I feel it. Yeah, it's trying to stabilize. There it is. Yeah, so I got all the rudder in there.
Yeah.
Cool. Okay.
So those are your tools to descend faster. But it makes it super simple. You don't have to worry about doing a bunch of configuration changes. They're all in your hands already, ready to go. Especially that drag is very easy to come in and out of drag as you need it.
In the next episode, we'll share all the airwork, including steep turns, slow flight, stalls, and landings in the real airplane. And in this one, we're addressing the main questions that have come up so far regarding batteries and charging.
I want to show you something else while we're here, where we make batteries, which is pretty rad. So this is where we make the battery packs for the airplane. So this is what it starts as, little 21700 cell. That cell comes through this robot who picks it up, measures the impedance, the open circuit voltage, the mass, the geometry, everything about that cell, and drops it into a tray that comes down the assembly line and goes from a bunch of cells sitting in a tray, epoxy to a heat sink, comes down here, a bunch of sensors are added to it because it's really important you know everything about the battery, goes into a welding system where it welds everything together, creates about a 50 volt module before it comes down to the end here to get a 830 volt battery. So Mary, tell this fine gentleman what you're making here.
The blessing and the curse of how much access I got here is that some of what Mary told me, ultimately I couldn't share. So I had to get a little creative in editing.
Once they come out of the bonder, they are, and what I do here, more protection from any thermal runaway. Once they do that, which is where we throw a ton of energy into this to make sure that those, which is exactly what they're supposed to do if there's any issues. After that, we come down here and we moves on down for end of line QC, and then it's ready for the pack.
Wow. I'm Steve, by the way.
Mary.
So all that to say, or not to say, these are obviously very special proprietary aviation batteries. And with that in mind, one of the supporters of the Flight Chops channel, also working on some really cool battery tech, is EarthX. We're currently running a giveaway on Instagram, and I'd love for you to check that out.
Down here, all those modules, once there's 11 of them, they get built into a pack. So that pack is about 500 pounds, 550 pounds, and that goes up to full voltage, 830 volts. There's 5 of those in a battery in an airplane. So those 5 battery packs, I'm going to show you in an older prototype aircraft over here how they go in. So that whole pack right there gets popped up underneath the airplane. You see there's 5 spots. So right up in here, there's this huge gap right here. And this is where the battery clicks in underneath here. So 5 of them. And as aviators, we know CG is really important. People ask why there's 5, why there's 4, why there's 6. It's so you can take the center one out, and if you look up, we're at the 25% chord position of the wing. We're at the CG right here. Right. So we can now trade mass or payload for energy by putting that back here. If you have a rearward CG, you take out number 2. If you have a forward CG, you take out number 4. And so now we have this longitudinal flexibility that we've never had before with our fuel.
So we got to do a lot of real flying, and I'll be sharing stick time in the actual airplane, but the simulator training with Nate was very effective at getting me to understand how this airplane felt. So I wanted to share my first experience working through the pattern procedures and landing.
So in the pattern, I like to kind of generally what I do when we're set up downwind, we'll do our before landing check. It's pretty complicated. We don't have flaps, we don't have gear, we don't have a prop, we don't have anything else to adjust. So we're in landing configuration. The only thing we're going to check is we're going to pump the brakes, make sure that they still have pressure.
And what, just by the pedals not being squishy?
We'll make sure that the light's on and that our seats are belted. So you're looking a little high, you're looking at the pappies are a little high now, so go and pull it to that drag region. And then just maintain your airspeed.
I just feel visually, I feel low, but
yeah, it
really flies like an ILS like glide.
Yeah.
Okay.
Engine off, it'll fly about a 4-degree glide path.
Amazing.
The cool thing about doing a lift plus cruise design is we can optimize the propellers and the whole system for doing their job. So the lift propellers are optimized to do the lift portion, and the cruise propeller is optimized to do the cruise portion of flight. Versus if you use the same propeller in a tilt rotor design, you can't change the twist of the propeller. So you're always taking a drag hit in cruise flight, or you're losing hover performance. So we take a little drag hit by parking those things.
But if anything, this airframe glides too well as it is. This is us turning base to final in the sim, and Nate's about to tell me that I'm high, even though I feel low.
Even at this, we're probably going to land a little low.
Wow. Because I don't fly by the pappies. Most things I fly because I'm steeper.
Right.
And we don't slip in this thing, I guess.
You can.
Let's see how this goes.
We'll just do it straight.
Because to me, this looks like what I would definitely want to fly. I would not want to be shallower than this. Like.
Yeah, this looks good.
Okay.
We're gonna. You're coming down onto the normal glide path now.
So get it out of the drag.
Yeah, you could throw it to 0.
Because we're at 800 feet per minute. And I want to get my feet ready to think about pedals, but no.
Yeah, but not on the pedals.
So okay, we're thinking about it, but we're not there.
So now, as we get down here, your goal is to get down to 5 feet and then just hold back pressure just to hold the nose off. And it's going to land, it's not a full stall buffet landing, so just a little back pressure,
let's
down the runway.
Let's get in there gently.
Yep. And just kind of hold this attitude and let it settle. A little more pitch. A little left to hold it on center line. It's looking great.
I'm having a hard time with yaw.
That was beautiful.
Okay.
And then all the way to drag.
Yeah.
Yep. And now you can get on the brakes. And it's just differential braking, still using your yaw in the hand to help correct back to center line. And we'll just do a full stop. That was awesome. That was super smooth.
Wow, good coaching. Cool. All right, so I don't want to cook my brakes. I was in the meeting for that. It feels heavy, so you can kind of feel the weight of it. That's cool.
So one of the main questions that have come up since I started sharing episodes about this is how this airplane charges. They really tested it in the field during the road show, flying it all the way across the country from Vermont to California. So with that in mind,
we'll go ahead and get the plane charged up. We'll just turn the low voltage on so that we can see what the charging's doing, so we can talk you through it. Not required for a charge, but all our batteries are coming online here, so good communications there. And then to charge.
So the electric chargers are out here. They're all over the east side of the United States. And people are always surprised to say, you're flying all over the place with electric airplanes? And then they start noticing the chargers, which are not branded. They're just white boxes where you can charge a car, an airplane, any number of airplanes on it. And you can traverse all up and down the east coast of the United States right now on electric airplanes.
When you're building an electric airplane, you can't just build the plane. There's no charging infrastructure on, out in the world. So we have to build the charging too. So we think about the whole system here at Beta. So we're charging, pilot training, and aircraft operations. It's as simple as charging, an electric car. I'll pull up my Beta charging app, scan the QR code here, hit start. Now it's starting up, and then I can take our cord. It automatically reels out, or when you hold the button.
The electric chargers, we have big stationary ones that are connected to the utility, and then you have ones that you can carry with you, and you can plug into a 480 volt outlet that usually powers a jet GPU, ground power unit.
So we built this as a in-hangar charger, so it just plugs into a normal 480 outlet that lots of hangars already have for running jet GPUs or things like that. And then it ups the voltage and converts it to DC so that we can plug it into a normal CCS1 adapter.
It's been a lot of discussion about what the charging standards should be, where they should go, who pays for them. We figured it out. We have about 60 sites right now at different airports where these chargers exist, and it's growing rapidly. I think we doubled the number of chargers last year even.
Who else is going to be using them?
Everybody building electric airplanes and ground vehicles. So like here at the airport, they traded all their gas burning trucks in for electric trucks, and they charge on our chargers at the airport.
And we open up our charge door here. Then we'll see it'll take a couple seconds here it's talking to the vehicle now, figure out what the batteries are.
Green, I guess,
Yeah, so now it's initiating the charge cycle, it's blinking, turn green, so now we're charging.
This is a non-liquid cooled cable, so it works in all environments. And then there's this pay-in system that makes it so people don't drag it along the ground when you put it back in. So this is what a fast charger for an airplane looks about 1.5 times the power of like a Tesla supercharger.
So when this thing goes cross country, are you going to like carry one of these?
Yeah, so we'll literally put one of these in the back of the plane, and anywhere that has a 480 plug, we'll plug in and use power from the FBO.
And it's different than a car charger because it has to be super reliable. So we modularize all of the power electronics. So when you show up and plug the airplane in, there's no interface, there's no screen, there's no questions. It does vehicle ID, senses the voltage, starts charging. Then it worries about whether you're going to get billed for it and all that kind of stuff. Because the most important thing we do is get the airplane back in the air.
So now all the batteries are connected. We can see currents going in, and we're charging right now at 100 and 200 kilowatts. So this charger is capable of up to 320 kilowatts is what this charger can do.
Wow, that's awesome. That is like a car.
Yeah. And it's, vastly different than what you saw on the road with the truck. How easy that is just to pull up and plug in and charge. And a full charge will take about 45 minutes on this charger.
Aviation is wildly different than automotive. One of the things is these are publicly obligated lands. You don't get to say, I only fuel Gulfstreams but not Falcons or Cirruses and not Cessnas. You have to fuel everybody. So no, you don't put a proprietary system on a publicly obligated airport.
That's awesome.
We want electric aviation to take off, and the best way to do that is to enable everybody in the industry to do well. It's not a win if only we get certified and only one electric aircraft's out there in the world. Like, it won't get adopted. We need the whole industry to come up together and rally behind it.